Okay, in this example, I'm going to show you how to calculate the voltage based on a couple of point electrostatic charges. Okay, so here we have a 2 microcoulomb charge and a negative 3 microcoulomb charge, and we're going to just find the voltage at some arbitrary point x in between the two charges. So we'll say the point x is 8 centimeters from one charge and 5 centimeters from the other charge. And then we'll see how we can use voltage to determine how much energy would be associated with placing a specific charge at location x. So let's find that voltage first. I'm going to call this charge A and this charge B just to keep them set straight. So for A, I can find the voltage from a point charge. We recognize that the voltage is kq over r. So the constant times the charge that's generating the voltage divided by the distance to that charge. Again, this is a scalar, so I'm not going to get concerned with direction, but I am going to maintain my charge here because this scalar can be positive or negative, so I want to make sure I pay attention to that. 9 times 10 to the 9. The charge here, remember that microcoulombs is 10 to the negative 6. Divided by this distance, 8 centimeters, but remember, be careful here, we're using standard units, so that has to be 0.08 meters. And I get a voltage, 9 exponent 9 times 2 exponent negative 6, 0.08 of 225,000 joules per coulomb. So that's from A. B. Again, the same formula. Here we have a negative 3 times 10 to the negative 6 charge. Remember with these scalars that this negative means above or below our zero reference point. So unlike when we were doing these calculations with forces, where we interpreted the direction later, and so we neglected the signs, at this point I'm going to make sure I'm including my signs so that I realize if I'm above or below that zero energy reference point that I'm comparing to. So here I'm going to use negative 3 times 10 to the negative 6 instead of just 3 times 10 to the negative 6, because I'm not going to interpret sign or direction later. I'm going to interpret it right now and make sure that I do this calculation correct. Also 5 centimeters in standard units, 0.05 meters. And I get 540,000 joules per coulomb, and that's negative. And so remember, with voltages, I can find the total voltage by simply summing the individual voltages. So I got 225,000 and negative 540,000. And so my overall voltage is negative 315,000 joules per coulomb. So that's my potential of energy, not my actual energy associated with the situation, because I don't know what will be placed at this. This is just how much energy this system has the ability to create when I place a charge at that location. So let's place a charge at that location and see what the energy actually works out to be. Here we're going to place a positive 2 microcoulomb charge. So my energy, electrical energy, is going to be equal to my voltage times my charge. You know what, let's stick with the U for energy so that we don't mix it up with electric field. I know I used a U there, but that represents electric potential energy. I just don't want to mix it up with electric field. So my voltage is negative 315,000 joules per coulomb. And remember, microcoulombs, 10 to the negative 6, 2 times 10 to the negative 6 coulombs. and I get 0.63 joules of energy. Negative. So the negative here means that by putting that 2 microcoulomb charge there, that 2 microcoulomb charge would actually be attracted to that location. That makes sense because it's closer and 3 microcoulomb charge is bigger. So the negative charge is dominating this situation, so the positive charge is attracted in because the positive charge is attracted to the negative charge, which is the more important one. So what does that mean then? That means that this was an attractive situation. Energy was released when this 2 microcoulomb charge was attracted to that location. We can almost think about this like a ball that's rolled into a hole. So as that 2 microcoulomb charge went to that location and produced that negative energy, it's like it fell into a hole where energy then would have been available to other forms, likely kinetic energy, or the motion of these particles. So as that 2 microcoulomb charge approached point X, it actually would have sped up, and that energy would have been available, say, for heat or whatever other form of kinetic energy could be realized by that microcoulomb charge going there. So that's what that negative on that energy means. It's now in a hole or below what we consider to be the zero energy reference point. So that's how you can find the voltage in any location. You simply find the voltage from each individual charge and add them. Once you have the voltage, you can multiply it by any charge that you want to put at that location to determine the energy. And then if you get a negative, that's what that means in terms of being below or having energy available to other forms. And if you had gotten a positive there, that would have meant it required energy to put the charge at that location.